F5. There. And I presenter. Okay, so let me make sure you guys can see my presentation and hear me correct, right?
Yeah, I can see that.
Okay, perfect. So I think we're gonna go all the way back from before break. I think we left off on reclosers. So I think we left off, we had gone over some of the different components on this particular recloser. Reclosers, like breakers, they've got a handful of different ratings associated with them. They have continuous current ratings. They've got interrupting ratings, voltage ratings that they can handle. And then they've also got, mechanical ratings and reflowing ratings, all sorts of different ratings. So I've got these highlighted here, and I was just kind of putting it there maybe as a maybe as a comparison to a breaker. They're generally smaller and cheaper than breakers. They usually wouldn't have quite the interrupting rating of a breaker, but oftentimes they'll get the job done on a distribution system. So they're pretty common. This here is a pretty typical recloser controller. This in particular is a 651R. And usually this is how you get them, right? They come in these cabinets from the manufacturer. You can see this one here, right? It's got a mount to put it on a pole. They usually get their power, up from this voltage up here. You can see there, right? We got a little PT that'll give us voltage. You can also see if we do lose power, we got some battery backup, and a few other things for convenience, like an outlet and such. This recloser controller is very, very similar to a protection relay, kind of like one of the ones you would see in the lab. It's got some unique features to it that make it just a little different at times, but at a fundamental level, it's very similar. You can even see, right? It looks similar. So, reclosers have some unique curves to them. You probably wouldn't find in like a 421 or 451. And they're really meant to mimic some of the older electronic reset reclosers, which even those ones, right, were meant to mimic some of the way older electromechanical type characteristics. And I highlighted some of these typical ones that you would see in the state of Maine. So I had highlighted here, curve 105, 117, 113, 131. You can see those here. And you can see here, these are actually called fast and slow curves, which we'll get into as part of like a fuse saving scheme. But curves 1 and 1 fast would be for that phase element. And then you got 2 and 2 fast would be for the ground. So, we talked about the recloser controller. We talked about the recloser, right? This is obviously at the top of the pole, as we can see here. This is usually down, right at the, good height for a technician to work with. So what we've got is what's called an umbilical cord. And this is really what gets all of the information and power and, commands back and forth between the recloser and the recloser controller. So a little bit of a still block diagram here. You can see you've got your recloser. It's got that 42-pin control cable. We can see right there. You can see where that plugs into the recloser. But not always a 42 pin. There's a bunch of different connectors you can buy. But that's a pretty typical one. And then up at that recloser, like we talked about, that they had that voltage transformer, and that brings power to your recloser controller. So some of the typical things that are going to be on that umbilical cord, right? It can bring digital statuses, open close status, the CT currents, PT currents, trip commands, close commands. There's all sorts of different things that you can see on the wiring for that umbilical cord. From the instruction manual, this is a pretty common pin layout. This one in particular is for that 42 pin umbilical cord. Again, like I said, there are other umbilical cords that you can get. So this one for particular, what you can see here is on the right, it has the recloser. And on the left, it's got the recloser controller. So everything in between is one of those cables on the umbilical cord. And you can see of the 42 pin controller, which pins it would associate with. So for the recloser, it looks like this one, it's got two PTs, one on the source side, the other on the load side. And these PTs are actually, they're called low energy analog PTs. Really all it is, right, is you've got two capacitors and you grab that middle point to get a voltage. It steps down the voltage, right? You got a voltage divider to step it down to an acceptable level. So we got phase A, B, and C on the load side. And then, we got phase A, B, and C on the source side. So we got voltages. You can see here we've got some CTs. So we know the current also. That's going over to the recloser controller. So that's a lot of our analogs. And then over here, we've got a very similar pinout for trip coils and closed coils. That one's a little interesting. That one actually relates it to particular relay settings. So those are relay settings that you can actually program, and it kind of shows how that would go to I guess a internal transistor. And then, that's kind of what drives that physical circuit. So yeah, I guess that's reclosers. Line sectionalizer. It's a protective device that automatically isolates fault sections of a line from a distribution system. So it's a little bit different than a recloser. I would think of it as being a device that is smart, like a recloser, except it doesn't have that fault interrupting capability like a recloser. So really what it would do is it can determine that the fault happened, but it's going to wait for the voltage to go away, right? It's going to let an upstream device trip. When the fault current goes away, then it will open, right? It doesn't have to interrupt that fault current itself. And then the upstream device can reclose, it can restore that area, and then this can stay open need be. So it can do some more functions. It can count the number of operations of the upstream recloser, right? It can figure out we lost voltage, we got it back. We lost voltage, we got it back. It can tell how many shots the upstream device is at and make decisions based on that. So it's typically set to open at one less operation than the recloser upstream would block out for. So the whole goal for that is, let's say we've got a breaker, call that a sectionalizer, and then we go to a distribution line. And let's say, we've got some taps. We don't want those people to lose power. So let's say a fault were to happen right here. This guy is typically set to 1 less reclose than the upstream breaker. So what would happen is we would have a fault right here. We would have a trip. This guy would count, right? It's not going to be able to it's not going to be set to interrupt that, but it'll count. Then that'll reclose. Let's say this is set to, let's say it's set to 3 recloses. Just a hypothetical. So this will trip, it'll reclose. Then it might trip again, and then reclose again. So this guy would be set 1 less. So if this trips again, during that open interval, this guy would know to open and stay open. It would isolate that part of the fault, and then the breaker would have the ability to reclose. Because this was open, the fault current has gone away. This this recloser breaker, whatever you want to call it, will then successfully reclose. It'll restore power. It won't trip back out, and everybody's happy. So the sectionalizer is just a cheaper way to do that, because that interrupting capability is probably the more expensive part of a piece of equipment. So automatic reclosing. I know we've talked about it a lot. Maybe we've gotten a little bit ahead talking about it, but it kind of plays into a lot of the other things that we've been working on. So I think we said up to 80 to 90% of faults on overhead distribution lines are temporary in nature. Think of that squirrel getting fried and then falling off. When we do have one of those temporary faults, it's good to try to do an automatic reclose, because we might be successful. I did want to note, successful reclosing is much less common on underground lines, so probably wouldn't have reclosing on underground lines. Reclosing is also much less successful, typically for equipment in the substation, like transformer is in the substation, bus work is in the substation. And that's just due because, you're not going to have vegetation, inside the fence of that substation. You're going to be within, lightning protection. So, lightning's not going to cause it. Usually if it's in the substation, fortunately, right, it might be personnel, like a boom lift. So everything we're talking about is going to be, think overhead distribution lines. So for distribution lines, these reclose attempts are generally time delayed, kind of like what we saw in the lab last Tuesday, right? We would do that test trip, and then maybe 10 to 15 seconds later, we would do that reclose attempt. Right, good to give that squirrel time to really finish burning and fall. And then multiple reclose attempts may be used for various different reasons. Sometimes it is to coordinate with different sectionalizers or upstream or downstream reclosers, or to work with fuse saving schemes. That's pretty common to use multiple attempts. And then sometimes people want to use reclosing just for ground faults. They might do that, right? Because even statistically within that 80-90%, it's an even much higher percentage that you're going to successfully reclose for ground faults. Phase faults, maybe less, but that's usually a utility preference. Some like to reclose for all, some just ground. You got to work with them and get a feel for what they want. And kind of to go back with what we were talking about, this really just applying for overhead distribution lines today. There's a lot of situations where you don't want to reclose, and a lot of situations where you will actually block closing or reclosing. Um, so um, one would be lockouts, right? If you had a breaker failure lockout, right, you got a bad breaker, don't want to reclose if you got a bad breaker. The bus fault that we talked about, right? It's in the yard. So unlikely that it's a temporary condition like vegetation, lightning. It could be a boom, someone in a boom. Don't want to reclose for that. We've got that breaker hold that we did in class the other day, right? Someone may have a lockout tagout where we know that people are going to be working around energized equipment. Just turn it off to be safe. Another one, right? Tripping immediately after a breaker is manually closed. That is indicative usually of something called switch on default. We won't get into that. And then sometimes you can use 50 elements or 21 elements, and you can set it to only operate for a portion of the line that you don't want to reclose for, such as if you did have part of a line being underground and part being overhead. You could block for protection elements that are set to just see that underground portion. So that's fairly common. Then yeah, for a lot of these you can drive the reclosing to lockout, which I think we saw last Tuesday. And then yeah, we've got other supervisions for closing that don't include driving it to lockout. Sometimes you may only want to close on a hot bus behind you, dead line in front of you, or sometimes you can close if you got a hot bus and a hot line, but then you want to do something called a sync check, which means that really those sine waves are lining up with each other. So there's I guess there's a good amount to consider here. We're kind of doing an over a high level look at the whole thing right now, but a lot of details to consider there if you're doing different protection designs. So here's a pretty good I think flow chart from one of the SCL 451 manuals. You guys have got a 451 in the lab. I don't think we've got a lot of slides to go over, but this would maybe be the best use of our time. But this is pretty much the flow chart in the relay and how it makes the decision to move to the next step in its reclosing cycle. If you are going to develop relay settings for an auto reclosing scheme, this is something that'd be pretty valuable to work through. This is maybe more of a high level view of that sequence, maybe more generalized and a good concept to wrap your head around. So we would pretty much walk our way through through a reclosing sequence, and I think this helps to visualize some of the terms I've probably been throwing around here, as we've been working. So we'll start at the left and work our way through this. So we'll start in a completely normal situation, right? The breaker is closed, load is flowing, everyone's happy. Well, we get that initial trip right here at time, we'll just say, time X, whatever it is. So when we get this initial trip, the breaker is going to open, right? Come down here and it opens. So let's say that's going to be open for, let's just say 10 seconds. That 10 seconds is what we call an open interval. And that's a setting that we can define and say, okay, do we want it to be 10 seconds, 15? We can make that decision. Um, so the breaker can be open for a period of time, the open interval, and then we're going to have our reclose attempt. That's going to be our first shot right there. That's the term shot. It's our first reclose attempt. Everything up until there, the relay is going to be in shot 0. Well, let's say it was a permanent fault, and we pretty much immediately trip back out. Well, what's going to happen then? We trip, the breaker opens, and we start what's called open interval 2. Again, we can define that. Maybe we want it to be a little bit longer than open interval 1 was. Let's say, 20 seconds. Well, the breaker will stay open for those 20 seconds, and then it will have reclose attempt 2 or shot 2, and the breaker will close again. Well, whatever caused it is still there. So it trips out again, and we go into open interval 3, which we can see is even longer. And then we have that next reclose attempt, call it shot 2, and then it trips one last time. This particular recloser was only set to 3 reclose attempts. It's not going to give it a 4th attempt, and that's when it will drive to lockout. And that would be, shot 3. It would also be last shot. So, just a note that you can make decisions based on all of this information. You can pull these word bits from the relay, being shot 0, shot 1, 2, 3, or last shot, right? It knows that, you've programmed it for 3 attempts. You're on the 3rd shot. It knows that's the last one. And you can use this in decision making. You can tell the relay to do whatever you want to do. If you want an LED to flash to let everyone know, hey, this is your last try, you could do that if you want to. It's all customizable. Another thing to talk about is the reclosing operating cycles. This goes along with a breaker or reclosing or recloser rating. Because these things, right, you've got stored energy, you're interrupting energy. You can't just slam this thing in and out as fast as you want, as many times as you want. That's dangerous for the piece of equipment. So you've got the O, which is the initial trip of a circuit breaker. You've got your T, which is the minimum open interval on the first reclose attempt. The CO, which is a reclose and retrip. And then T, which is the minimum open interval for any following reclose attempts. And then you've got more reclose retrips. So the T, right, just the regular T, that tends to be a little bit of a shorter time duration because this breaker's been sitting there. It's got, stored energy that it can use. Right, it trips. When it goes to reclose, it's got that stored energy just ready to go. But it uses it. If you retrip again, well, now it needs to take time, build that energy back up, charge, and then it needs to have that time before it can reclose again. So that's why you have different times for that initial reclose versus following recloses. They give it that charging time, as it says right here, pretty much. So you can derate these times, based on, some of the capabilities of the breaker versus, the conditions. I've never seen it done. We usually just, follow the ratings as is. Um, so here is a pretty typical breaker nameplate that you would see. This one in particular is for a vacuum circuit breaker. Right, the interrupting medium is a vacuum. It extinguishes the arc just based on the fact that there's no oxygen. As compared to like let's say an oil or SF6 breaker. So again, we see a bunch of different ratings. But let's see, where is our reclosing intervals on here? There it is, right there, operating duty cycle. So we can see we would have an operate, an open time of 0.3 seconds, another operate, and then after that it takes 15 seconds. So let's say we have we've decided that we want to have 3 reclose attempts with open intervals of 10, 15, or 10, 20, and 30. Would that work? Does anyone think that would either work or not work? Well, come on, Shane, you should be looking at this every day. So this one should work, right? That 10 seconds is greater than our 0.3 minimum time, and then 20 and 30 seconds are both greater than the 15 second times for the following reclose attempts. So yes, the proposed times are acceptable. Okay. So it looks like we're getting into overcurrents. Good point to maybe take a breath. Ask, anyone have maybe any questions related to the reclosers or automatic reclosing? All right. Well, sounds good. So we're going to get into some overcurrent considerations. We'll start with instantaneous overcurrent. All right, there's never anything instantaneous, but we'll call it, without intentional delay. We always got to think, it takes the relay a little bit of time to detect it. It's usually about a cycle. It takes contacts on the relay time to actually close, takes the breaker time to open. So nothing's ever instantaneous, but preferences for instantaneous elements tend to differ by utilities. They seem to always have their own standards. I think I kind of skimmed over this top note, but they're always set to underreach downstream reclosing. And that's just because, we need to coordinate with that downstream reclosing. If we both open and we both reclose, it usually gets you into not a good situation. So some utilities may choose to not use instantaneous elements. Right, there is some risk there. If the system gets stronger and it begins to overreach with time, you could overreach something that you didn't think you were going to overreach, and then you're gonna miscoordinate, and more people will lose power than what you want. Some may choose to underreach all downstream protective devices with or without reclosing. And then some may accept overreaching a fuse or relaying if reclosing is used on the upstream device and is not on the downstream device. I guess so what I'm trying to describe there, if it's tough without a visual, is let's say you had a breaker, you're going to go to another breaker. You've got a transformer, and then you can continue down the line, you've got other stuff. So sometimes it would be okay to have an instantaneous element that overreaches another device if that device does not have reclosing. So if the upstream device does have reclosing. So the example in question here would be, if a fault were to happen right here, and our instantaneous element were to be set sensitive enough to see that. Well, this breaker would trip. This breaker would trip. If this breaker does not have reclosing, it'll stay open. But this one does have reclosing. It will reclose, and then everyone will be happy because the line gets restored. So sometimes that'll be acceptable. Sometimes they don't want to. They don't want to. Take those risks, have those, those potentials for outages, and they'll just have the instantaneous element come up just short would be the plan. So, and then sometimes they don't want it at all because, as we install all that solar right behind it, they may think that they have it set just short, but 2 years down the road, right, all that extra solar behind us pushes us into it. And we may not have expected that. So, yeah, the preference is usually by utility, and you got to find out what they want. And then a typical setting of that would be 125 to 130% of the maximum phase or ground current for a fault at the location they don't want to overreach. So let's say this is the location that they don't want to overreach. If a fault were to happen right there, let's say we had 5,000 amps. Well, we don't want to operate for a fault on that spot. So let's set our setting for 6,000, right? That way we won't operate for it. We'll probably operate up to here-ish, but we're not going to operate for that. So, that'd be a pretty, a typical approach. So yeah, we'll do an example of that. And these are the biggest C examples you guys will be seeing on your homework. So, so the protection engineer has decided that they want to set a 50P element and a protection relay to 125% of the maximum fault current for the first downstream device on the distribution line. The maximum fault current for a fault at the first device, let's say the closest recloser, is 4,000 amps. So, okay, we can show that. We said recloser, so we'll draw that symbol. Put a little R. So, fault right there, we're going to see 4,000 amps. Recloser. So, we want to set it to 125% of that at 4,000 amps. That would be 5,000 amps primary. So we will not operate for that 4,000. It's going to take a little bit more. And then, as always, right, the relay is based on the information that it has. So there's a CTR of 240. So our setting would be, that 125%, 4,000 over the CTR of 240 gets us 20.83. Would be the setting that we put into the relay. And we got to take that CTR into account, just because those 4,000 amps, that's a lot of energy. That would blow any electronics to shreds, really. So we've got that CT that we talked about in previous classes. It'll be, let's say, 1,200 to 5, which is that 240 that we talked about. So it'll take that 4,000 amps and it'll reduce it down to a smaller value for our relay, and give it a value that's not going to blow our relay to shreds, essentially. But the relay does, when you pick your setting, it's based off that smaller value because that's what the relay is actually seeing. So that's why we're doing that. So some extra considerations. If you've got a non-directional phase instantaneous overcurrent element, it needs to consider phase and ground faults because a ground fault is going to have current on the phases, right? If it's a ground fault on phase A is going to see a lot of current. And then ground elements just need to consider ground fault current, or three-phase or line-to-line faults. Right, you're not going to have any 3I0, so it just needs to consider the ground faults. And then lastly, it might not make sense to use a 50 element if the closest device is very close to the relay. And by that I mean, let's say if this was a case where we're going to get 4,000 amps for a fault right there, but for a fault right here, we're only going to get 4,010 amps. Maybe just because this is a 200-foot line, right? Electrically, there's really no difference between this spot and that spot. It's next to impossible to distinguish faults in those two different locations. You may say that and be like, it's not worth it. So again, right, different companies will usually have different standards on how you make that decision or not. But it's a consideration. So to go along with those instantaneous time overcurrent elements, we'll talk through the inverse time overcurrent. So we've got a couple goals here with the inverse time. And by inverse time, what I mean is you've got a scale, you've got current as your independent variable, and then time as your dependent variable. Flip-flopped of everything you've ever done in physics. Right, time is almost always the independent variable. Not here. Here, time is the dependent. So you can see inverse time's got that characteristic there. It's got that curve. As current goes up, time goes down. That's just because the more current you have, the more energy you have, the quicker you can damage equipment. You want your relay to operate faster. So that's what I mean by inverse time. So really the goals of this inverse time is, I guess first off, right, you got to be set above your peak loading. Right? You can't be tripping on loading. Right? That's a normal operating condition. People need power. You can't be tripping them off for normal load. So that's your first goal. So usually you would figure out, hey, I got 1,000 houses connected to this distribution line. Right, the most power they could ever use would be 2,000 amps. I got to be set above that. Okay. Goal 2. You got to detect your minimum faults. Right, you got to protect the line. If a fault happens on your line, you got to be able to see that. So what ends up happening is, let's see here what I can get rid of. As your fault gets further and further away from your relay, you've got this line impedance. And the further you get away, the more line impedance, will reduce that fault current. So like, a fault right here, could be, 5,000 amps. You get a little further away, it could be 4,000. You get a little further away, it could be 3. But what you need to do is figure out, hey, this line is, 10 miles long. We're going to look at the very, very end of it. And we need to be able to determine that number. And we need to be able to see that number and, operate for that number. So what we end up with is a little bit of a window where we've got a minimum pickup, which needs to be above load. And then we got a max up here, which needs to be below min fault current. So this is for our pickup. And a pickup relates to where you start your curve here. So as you increase and decrease your pickup, what happens is this curve moves left and right, essentially. Sure, that's the pickup. We'll move it left and right. So you got to figure out what your min and max allowable pickups are. That's really your first goal. So after those two goals, our next two goals are related to coordination. As we talked about, if we've got that recloser, and a fault happens right here, we need to make sure that the recloser is faster so that it can clear it, and that the relay upstream is slower so that it can stay in service, because there's likely going to be other customers that we want to continue to provide power to. So with that, let's say you had a downstream recloser. Okay, I'll make that guy green. You got that downstream recloser that you want to be faster than your relay. You need to set your settings so that you're slower than them, they're faster than you, right? You got your fault current for this fault here. All right, you can see recloser is faster on that time scale, relay is slower. That's your goal. So your other setting to make this happen is something called a time dial. Your time dial is going to move you up and down. So as you adjust your time dial, you're going to go up and down. Right, you got to pick your pickup based on your sensitivity and your loading, and your time dial you really play with just to get that timing that you want. And then lastly, that last setting that you can use for timing is called your curve selection. And I think we talked about it a while back. You've got options like inverse, very inverse, extremely inverse. And basically what that does is it can change you from more of a flat curve to vertical curve to extremely vertical curve. It kind of changes that characteristic so that you can make it fit your application the best you can. a pretty good rule of thumb. Fuses usually best fit an extremely inverse curve. It's just the nature of how they're built. Reclosers, which often need to coordinate with fuses, will use curves that best fit, an extremely inverse. Um, and sometimes you would want a very inverse. That's usually a more typical setting that you would see in a transmission system. And then lastly, what you might see on here would be an equipment damage curve. So you might see an I squared T curve for a piece of equipment. So you might see what turns into a horizontal line like this. It's called an I squared T. All equipment has a damage curve, right? When shit gets hot, it breaks, right? How hot really depends on, the magnitude of that current and how long is it there. Right? A lot of current doesn't take long for things to break. And if, even if it's not a ton of current, if it hangs out for a long time, it's going to heat up over time. So you got that I squared T for damaged equipment. Usually you're going to want to look at the piece of equipment you're protecting and say, okay, I need to be faster than that damage curve because I don't want it to be damaged. So there's kind of your basic considerations for an inverse time protection element. So, yeah, we'll skim over the rest of that in the interest of time. It's kind of what I was talking about. Okay, so we've got an example here. So a distribution line has a peak measured load of 600 amps. And then also the minimum phase fault current is 3,000 amps. The minimum ground fault current is 2,700 amps. Imbalance has never been measured on the line. And then you got a CTR of 1,000. So we're going to pick a range of acceptable pickups. We'll talk about the rest. So if you look at 200% of the peak load, right, that's 600 amps. That comes out to 1,200. We need to be above that 1,200 amps. If you look at 50% of that minimum phase fault current, at 3,000, cut in half, that gets you to 1,500. Right, we got to be set below that. So our phase pickup got to be greater than 1,200, less than 1,500. Let's look at that CTR, right, because that determines what our device actually sees. So our setting needs to be greater than 1.2 amp secondary and less than 1.5. So that's how you're going to select your pickup. You're going to go through an exercise like that. Now, anything in this range is acceptable, right? 1.3 is acceptable. 1.4 is acceptable. It's kind of up to you to decide where in that range is acceptable. Now, when that comes into play is when we're looking over here, right? We're saying, okay, we got to be faster than that equipment damage curve. We got to be slower than that downstream recloser. Yes, anything from 1.2 to 1.5 is acceptable. I just know that as I change that, my curve is going to move left and right. And my goals are to be faster than damage curve, slower than recloser. What works best moving me left and right to accomplish my goals? So there's a little bit of discretion there. Usually it takes a little bit of fine tuning. But it's really up to you what you pick. If you picked 1.2, which was on the smaller end, maybe you got to bump that time dial up a little bit more. If you picked 1.5, which is, on the less sensitive side, maybe bump that time dial down a little bit. But that's It's usually up to you to make it work. And I think one of the toughest parts that people struggle with protection is oftentimes there is no perfect answer, right? It's um, right in math, right? 2 + 2 = 4, always, right? No debating it. The right answer in protection is not always a perfect answer. There's usually a number of things that are acceptable. You need to work within what's acceptable, but then within that, you do have some discretion as far as what you select. So um, people kind of struggle with that sometimes, right? Why'd you pick 1.3 versus 1.4? They were both acceptable. Yeah, but I like to, usually comes into play. Um, so yeah, after you find that acceptable range, your exact pickup, time dial, and curve selection would be best selected to coordinate with upstream and downstream devices. Um, ground, in the interest of time, we'll probably skim over. Very, very similar, except you've got, different margins. Same exact goal. The only difference is rather than operating on phase current, you're operating on that ground current. It's just usually more sensitive because, a peak ground current based on imbalance is usually much less than peak, phase current. um, so yeah, I did want to get into the cold load pickup because I think it's a pretty interesting function. Um, so, um, so normal loading has diversity, meaning that not everything is on at the same time, right? You're not going to have, maybe if you have electric baseboard heat, right? It's not going to be on at the same time as your air conditioner, right? That just doesn't make sense. Um, so when distribution um, has been de-energized for a long period of time, the load becomes cold, is the term. Um, and when that line is re-energized, the relay needs to pick up this cold load. And basically what happens with this cold load is everything turns on at the same time, or not, maybe not everything, but things that may not have normally all been on at the same time, more of them tend to turn on at the exact same time. Pumps got to start back up, heating systems got to start back up. Everything's kind of got to get back to that normal place. So yeah, some typical examples of that, right? Heating elements, if it's the winter, air conditioning, if it's the summer, right? On a 100-degree day, if you guys lose power for 4 or 5 hours, every one of your air conditioners is going to kick back on. If you lose power, then you get it back, right? How do we deal with that? So during cold load conditions, loading maybe 200 and 50% for example, of a normal peak load. So the challenges with that, we'll look at it mathematically here, but I think visually, it's maybe a little bit easier to work with. So everything that I had been talking about has a minimum setting, which needs to be above load. You got a maximum setting which needs to be below the minimum fault current. Like I said, everything in this range is acceptable. Challenge with cold load pickup, we still need to be set above that cold load. The challenge with it is now, okay, our margin, our acceptable window is getting smaller. Our acceptable window is getting smaller. It's getting smaller. Oh shit, what do we do now? Right? Our minimum acceptable criteria and our maximum have crossed, and we don't have anything that's acceptable. All right, that's a serious problem. What do you do in that situation? That's kind of, what we want to talk about with the cold load pickup. So yeah, how can we overcome that? There's more than one answer here. Does anyone have any ideas?
All of these is located in IE C237, yeah?
I think you're in here twice, Kia. I think you got some sound bouncing off yourself.
Okay. Thank you.
Yeah, I'm not sure if you've got maybe like two laptops or a laptop and a phone, maybe two browsers. I'm not sure, but it looks like you're actually in the meeting twice.
Yeah, because one of them is no voice, and that's why I'm using my cell phone.
Okay. Yeah, maybe if you can type it into the chat. You got some audio challenges there, so we can't hear you too well. But if you want to type it into the chat, we can come back to it. I'll go over some of the solutions there. We'll run into an example here. So one of the solutions, what if we change the pickup, but only when we know the cold load, only when we know that we have cold load, and only until normal loading diversity is restored. This concept is referred to as cold load pickup logic. So cold load pickup logic usually uses a separate 50 element, and torque controls the 51p element we previously set. So the curve and shape do not change, but instead is cut off to prevent the cold loads. So let's do the following. We'll use the 51p pickup we had before. Let's say we decided upon 1.4 amps. But now we have to set the cold load above a value of, let's say, 1.9. We're going to set this 50p element, but instead of tripping with it, we're going to use it in some custom logic and drive that 51p torque equation. So we're going to look at some logic. It can be a little tricky to follow, but we're going to start with an initial condition of the breaker just opened and the cold load pickup function is off. Note that we could have also used load encroachment. That could have also been used, but that has some of its own drawbacks on a distribution line where there's a lot of natural imbalance. So probably haven't talked about load encroachment. If you've done settings before, you probably know what it is. It's another option that's got its own drawbacks, but it's common to use also. Okay, so our initial condition, the breaker just opened, so we've got a 0 here, and cold load pickup is off. So we've got a 0 here. So if we've got a 0 here, we got a NOT gate right there. Right, the breaker is open. Right, we got a NOT gate there. That gets us to a 1. Well, where's this coming from? Okay, over here. So we got a 0 here, which means we got a 0 there and a 0 there. If both of those are zeros, this all passes through as a 0, meaning you've got a 0 and you got that NOT gate, which makes it a 1. Okay, so the breaker is open. We got a 0 right there. If that's the case in this situation, it's for 15 minutes. So if that breaker is open for 15 minutes, right? Let's say that 15 minutes is just a time long enough to, let your house get unbearably hot, right? On that hot day. If that breaker is open for 15 minutes, we're going to get to this rising edge trigger. We had a 0 here initially, which makes that a 1. And for one cycle, after 15 minutes of that breaker being open, we'll have a 1 right here. And that is what is going to turn on our cold load pickup. So after 15 minutes, our cold load pickup is going to turn on. We no longer have a 1 there, or we no longer have a 0 there. We now have a 1. So now we have a 1 right here. We're going to have that LED illuminate, letting everyone know that the cold load pickup is active. So we've got this 1 coming in. So now what happens is we've got a 1 here, which means we got a 0 there, but that's not going to pass through. We need the current to be above 1.9 amps in order to get a 1 here. If that current is above 1.9 amps, then our torque control will be a 1 and our element will be allowed to operate. So what ends up happening there is we've got our normal pickup. We got our normal pickup of 1.4. And basically what we did, I like to use the word snipped. We snipped off the back end of this curve. The curve didn't move, right? If we would have changed that pickup, we would have gone left, right. But we didn't do that. We had a separate element torque control it, and we effectively snipped it at 1.9. So now everything here is going to look the same. It's going to coordinate with that damage curve the same. It's going to coordinate with that recloser the same. We just snipped off that part of the curve and effectively made the pickup 1.9. So we've effectively made that pickup 1.9. So what's going to happen now is, let's say that current, right? It's unbearably hot. And we turned on all of our air conditioners. So we're above that 1.4, right? That loading, right? It really built up because everyone's air conditioner turned on at the exact same time. And then, everyone's air conditioner turned on at the exact same time. And then, everyone's room got more reasonable, right? And now your air conditioner is just turning on and off to maintain that. It starts to go back down. So that 1.4 amps that we talked about, and let's say that was, 1.9. Right, we didn't trip for that 1.9, we're happy. What happens here is it got up above that 1.4, and eventually it's going to fall back down and normalize where that 1.4 is more maybe appropriate. So cold load pickup is on. All right, we'll come down here. We've got a 1, right, because cold load pickup is on. And once it drops back down below that 1.4, right, we're going to have a 0. And we're going to have a 1. So then we've got a time delay here of 15 seconds. So basically what we've said is, the cold load pickup is on. We dropped below that 1.4 amps, and we've been below that 1.4 amps for 15 seconds. Okay, we got a 1 and a 1. What we're going to do is we're going to send a pulse, and we're going to have a 1 come through, and we're going to reset that logic. So now, after it is normalized for 15 seconds, we can turn that logic off and go back to our normal pickup. So now we're back to a 0 here. When we're back to a 0 here, we're back to a 0 here. That part doesn't really mean as much. I got a knock gate. We've got a 1. We're back to our normal pickup. And then the last kind of part to this is, what if we, close that breaker back in and there was a fault, and we've got this higher pickup that we can't see because it never normalizes, right? It's an actual fault rather than load. Well, we've got a 15-minute timeout here. So regardless of if it normalizes or doesn't normalize, this thing can only be active for a certain period of time before it resets itself. So, yeah, I guess a little bit of tricky logic, but I think pretty cool logic. If you're looking at something like this and think, oh, this looks interesting, I wouldn't mind being involved with something like this. Maybe relay settings are for you. You know what I mean? This is the kind of stuff I like to put together. And most protection engineers that are good at what they do, this is kind of the stuff that they like doing. So I think I had it on paint, but this is an actual slide for it. So the part on the left of the curve gets cut off, like I mentioned. The part on the right is active. Curve didn't change. It's more of a snipping, is what I call it. Okay. So changing speeds a little bit. We'll get into a fuse saving scheme. As we talked, most overhead distribution faults are temporary. Now, once blown, a fuse needs to be replaced by a technician. It takes them a long time to get out there. It's expensive and maybe challenging for them to find what happened. Right, it's just time consuming and expensive. So it results in longer outages and it's a burden. So if an upstream device with automatic reclosing operates before a fuse minimum melt, the fuse can be saved. It's called fuse saving. If the upstream device operates first, additional load may be lost though. So any ideas how we could overcome this? Well, we had a slide for it early on. It's a fast curve and a slow curve. Going back to some of our previous examples, we had the 3 reclose example from a previous slide. We can have a fast curve that is supervised by that shot 0 and shot 1 that we talked about. And then we could have a slow curve that would only operate during shots 2 and 3. So yeah, pretty easy logic for it there, right? It just goes to those torque equations. So here's a pretty good example of that fuse saving scheme that we talked about. This curve right here, we'll say operates on shots 0 and 1. This guy will operate on shots 2 and 3. So let's say the situation, let's say that wasn't a recloser. Let's say that was a fuse. That's more what a fuse looks like. And it's got its own load down here. So if a fault were to happen right here, let's say it was a temporary fault. Temporary fault happens right here. That fuse, if it blows, those people are going to lose power and their power is going to be gone until a technician gets out there and replaces that fuse. So kind of what we can do is we can not coordinate like we talked about before. but we can actually make this guy faster than the fuse. So when that fault happens, this device will clear that fault and the fuse will be saved. So we'll have that fast curve that's faster than the fuse, so that for this fault, you know, we're saved. And then we can have a slow curve so that if it is a permanent fault, we can swap to that slow curve. The fuse can clear it because the fuse has to clear it because it's a permanent fault. And the fuse will operate if these people lose power, but we can continue to serve power to these people over here. It's the concept between that fuse saving and a fast and slow curve. So, right, we can see this here. Curve 3 is going to be faster than the fuse. It'll save it. We'll give it 2 chances. Then we're going to swap over to this slow curve. And then, okay, now fuse, you got to take it. You're the guy. We need to continue to feed power to our customers, so you got to take it. And technician stinks, but they're going to have to go out and change that fuse. So yeah, like I said, there's the logic for it. 2 different overcurrent elements, one supervised by shot 0 and shot 1, and then the second one is always just active. It kind of gets masked by the first one. So once the first one goes away, second one, we just have that set to a 1, and it would only operate for higher order shots. So yeah, I guess that's fuse saving. Oh, I hate doing it. We're gonna get cut a little short because we got 1 minute left. Yeah, I came about 10 slides short. I did want to use that time, maybe see if you guys needed any help with the homework. Give you guys maybe an opportunity to yeah, ask any questions if you had any. I think most of the homework really revolves around these overcurrent settings. So. Anyone? Did Paul get you guys those Excel spreadsheets that Shane asked about last class?
Take a quick look.
He said he did.
The relay fuse coordinator and relay coordinator spreadsheets.
Yes. Yep.
Yeah, I see them under this class.
Okay, perfect. Okay. Great. So I'll give you a quick rundown on that because you'll have to use them for your homework. You guys, for your homework, are going to do some calculations. The calculations will help you figure out your minimum and maximum acceptable pickups. And then from there, you're going to do some relay coordination, right? You're going to play around with those time dials and curves to get things to coordinate. So really your input data for this spreadsheet is these up here. You've got your settings for relay 1, you've got your settings for relay 2, and then you can specify a fault current. So you can see on the curve here right now, the fault current is more current than those instantaneous settings. So therefore, both relays operate without delay. We can see that right there, right? They both operate in 0 seconds, and the difference is obviously 0 seconds. So if you play around with this stuff, like you could either, increase your instantaneous element, your time dial, all these different things to get different results. A quick one, right? If I were to change this fault current, let's say to 2000 amps, you see how that moved over? Well, we went out of that instantaneous region, and now we're in that inverse time. and we can see, okay, relay 1 now operates in about a half second. Relay 2 operates in about 2 seconds, and there's our time difference. But what we can do then, if we want to, is play around with these settings, right? Maybe I want to change my time dial to change that time. Well, you can see, okay, you can see that moving on the curve, right? And you can see your operate times changing. The goal of the homework really is to do calculations, figure out your minimum and maximum pickups, right? You can play around with your pickups within those acceptable ranges, and then you can also play around with your time dial and curve selections to change your operate time to give the the margins that it asks for in the homework. And then lastly, right, pick your settings, and I do want to see those settings selected and entered into Accelerator with snips of those settings. So I think it's a pretty good assignment. I would say it's pretty similar to what I would expect out of an entry-level engineer, someone that, maybe we hire them in May, and, the expectation is that they can do this, in June. It's through Excel, right? It does exactly what Aspen one-liner would do. Aspen is very expensive, and this is free. So here you go. Hey, I didn't know you guys actually had an Aspen license, so that's pretty cool. But if you wanted to, you could do this in Aspen also. Totally an option since you guys got a license. But you got this if you need it. So yeah, let me know if you guys have any questions. I definitely recommend reviewing those last 10 slides on your own. Looks like it gets into sequence coordination, which is kind of an extension from that fuse saving scheme. Distributed generation, talks about that a little bit. Some normal arrangements, inverters, utility considerations. Okay. So yeah, a few more items, but I don't think any of those items will be on the homework. So yeah, if you guys have any questions, you got my email. It's due a week from today, I believe. So yeah, have a good one. I probably won't hear from you guys again unless I bump into you. I'll be at the what is it there? The Industrial Advisory scholarship thing tomorrow night. I think I'm presenting a scholarship. So might run into some of you guys there if you guys are going to be there. But yeah, if I don't hear from you, good luck with everything. I'm sure I'll see you guys in the professional world when your time comes. So looking forward to that.
Thanks, Leo.
Yeah, thanks.
Yeah.
Thank you, Leo.
All right.
Appreciate it.
See
Thank
you guys.
you.
Bye-bye.
Call from 19059639118.
Okay.